And I would like to finish off the Friday class with a summary. A summary for the factor calculus. What is all the formulations and how they can relate with each other. Okay, so that will be the I think the final class. And of course, in between, I will adding some exercise. Of course, in a few days, I will give you maybe the answer key for some of the questions. I'm trying to make out some questions that is a typical like in the examinations finals factor calculus. But anyway, we are going to back to this part. Last time we have at least I show you that we have this definition for Stokes theorem, right? So basically, at the beginning, the orientation should be assumed, and what you need to remember by default, the orientation, like if you see the person they are walking around, the positive will be we call the clockwise rotation. That will be the positive oriented. Or if maybe the given information doesn't really give the rotation in which way, like counterclockwise or clockwise, by assumption, by definitions, you can assume that it will be positive. Or you could say it will be counterclockwise. So first is we could see the idea from here. We can sometimes we can write, like for example, if we have the curl f and then dot with the ds. The ds is the segment, okay, or length. Sometimes we can write not just with line integral. We can write with, usually we can write like this with the partial s or Leibniz s. They are the same thing. Sometimes they write in these forms. So instead of oriented surface s, we can write as the partial s. Or if the surface s is flat and lies on the xy plane, has upward orientation, and then we can write an unit normal. Suppose that this is k, that unit normal. Then we can write the line integral f of the r. We can write the Stokes first, curl f dot ds, and then we can write the curl f, and then exchange the ds with the k. So because this is a flat surface, so we can write the curl f dot k dA. And basically this is what we have here. This is what we have before. This is a factor form of the Green theorem. So Green theorem is a special case of Stokes theorem. Okay, so let me write here. Green theorem is special case of Stokes. And the theorem itself, the Stokes theorem, I think in full explanation, it's hard or difficult to prove, but intuitively we can see how it can relate. And for example, this part here, the last part, we can prove by taking this picture here. Suppose that we have assume. So let me write here first. Okay, assume that the S, surface S, is defined by the equation of the Z. Okay, just a normal equations. And then G we define as the has continuous second order partial derivative, which means that we can derive or partially derive this second time. And then D is simple region, which boundary is the C1. You can see the picture, okay? The C1. That the C1 corresponding to the curve C on the surface S. Okay, so you see, it's supposed to be like heavy wave like that, this one, and when it projected to x1 plane, this is basically this C1. And then if we have the vector field F, and let me write this like a standard PQR, like we did in the green theorem. So let's use the same variables and letter. So PQR, and all the partial derivative PQR, they are all continuous. So PQR, we can say this partially derivatives are continuous. Okay. So we can apply the formulations, which we can write the curl F dot ds. Okay, we can apply curl by taking the del and then cross with the F. Okay, so taking curl F, I will write directly the results. Okay, so but I hope you know the curl. Okay, basically it's a cross product. So we may have, this will be double integral d. Okay, basically this is taking you to this part here, which is the curl. And then we have the negative. So I will skip the cross product steps. This is the result, the del cross F. And then taking this to I think we can write all. Okay, and then the last one, since we have the only two variables x, y that we can partially derive. The last one is z. So we have now this. We are going to take this with respect to the dA. And then we evaluated this at x, y, and z will be the function of two variables x, y. Okay. So we are taking x with parameter x. We can say that. So taking x of t, y y of t, and then taking the parameter from A to B. Okay. So this is, suppose that this parametric, let's say for C1, okay, parametric for C1. Then for C, okay, C1 means on the xy plane, and parametric for C, parametric will be x and y still the same, but now we have z, which is a function of two variables. Okay. So this will be g, x of t, y of t. And of course, this will be started from A to B. Okay. Okay. Now our goal is to take this definitions on the curl f.ds, which we have this double integrations with respect to the region D, area D, and then we are going to focus on the left side of the equations, which is the f.dr. So basically, we are going to prove that this right side will be equal to the left side. Okay. So this will be the curl. Okay, this is the curl, all of this, and then let me finish this off. Okay, and then the integral, line integral f.dr. Since f is pqr and r will be, or dr will be r prime, okay, so we can write this with the additional parameter t. We can write this will be, after we dot, then this will be let me write here. If f is pqr, and then r prime t is let's say dx dt, dy dt, and then dz dt, and then we basically dot this two, and then integrate all with respect to t. And basically, because we define that the z is a function of, so z is function of two variables xy, right? Which means that we are going to partially derive z with respect to this x and y. So we are going to expand this dz dt. We are going to expand. So this will be, so for p and q, they are still the same. Let me just write that part one more time. And this one will be, we take another chain rule to connect this with x and y, okay, because they are a function of two variables. Okay. And then this will be dt. Now the next part is we are going to combine dx dt, and dy dt. Basically, we are groupings together and then try to make simplify. So this will be integrations a, b, and p plus r dou z dou x, and this will be dx dt. I hope you remember why one is d, the other one is partial. If you remember the chain rule, we can see that from here, we can write that z is getting x and y, and they are basically function of t, right? So every time you have a branch like this, you write the partial, But if you only have a single variable, you write d, right? And that's how we get this, right? Okay. Okay, and then we plus this q plus r dou z dou y multiply with dy dt, and then all together will be multiplied, or with respect to the integration with respect to dt. Now, if we want to change this integration AB into a line integral, we can do that as well. So, for example, we are going to write back into the C1, the curve 1, which means that suppose that we take this into line integral with respect to this C1. So basically we write just like the line integral equations that we have. So p plus r, and then this will be dx, and then plus q plus r dou z dou y, and this will be dy. Which in the green theorems, this will turns out to be the region D. Okay. And we are going to partially derive this. So I will write the q on the front so that it will be similar to the green theorem. And then this will be minus and then all with respect to the area of that region D. And then we finish off this partial. So we are going to partially derive q r dou z dou y, and then partial derive with respect to y for p, r, and dou z dou x. So again, we are going to take the chain rule, and then remember that the p, q, r, this is a function of x, y, z. But z also function of x and y. So let me write, and it's quite long. Let me write here, over here. So hopefully I can write the whole thing in one page. So this is a q, and then this is partially derived, okay, and then plus or minus here, minus the partial y. So this will be the last part. So basically they are having the same pattern, and we have, this is y and then x, and finish, and this will be with respect to dA. And if you see that we are going to see that the at least some of the terms will cancel out. For example, these terms is cancel out, and what else? Q, P, and this one is also cancel out because they are the same. So we can cancel that part, and basically, I was just showing you that at the end we have that the line integral f dot dr will be equal to this double integral or the surface integral curl f dot ds. Okay. I think it's better for us now focus on how to practically taking this theorem into applications, and hopefully I can have time for identification which part that we need to emphasize. Okay. Because sometimes because we deal with some curve and sometimes we deal with the polar curves, so sometimes we need to convert some to polar, or perhaps we need to parameterize into adding the parameter t or theta. Okay, so, and we need to know which when is the time. Okay, so this is basically just showing you the process that they are basically connected. The f dot dr is the surface integral curl f dot ds. Okay, now the problem here, if we look at this, but basically this is like a simple problem, but I would like to just to show you how to deal with this. So if we want to evaluate this, question is the integrations, line integral f dot dr, and we have f. So practically we can find the curl, right? We can find the curl f, and then c is the intersections of the plane y plus z equal 2, and then cylinder x squared plus y squared equal 1. So we have a cylinder, and then the curve is slicing the cylinder, okay? And then it's making up the plane y plus z equal 2, and then we have the cylinder x squared plus y squared equal 1. And then you also see that the direction is counterclockwise. The orientation is counterclockwise. So basically we are going to use the formulations directly. Okay. So first is taking the curl f. So taking the cross product of this basically this vector field. So taking I, j, k, and then take the determinant. Sorry, this is supposed to be the partial y and then partial z. So remember that the curl is nabla cross the f, right? Okay, and then we compute this. Okay. So taking the so some part of this curl will be 0, right? Like for example, partial y of z, that should be 0. Okay, so some part of will be 0, and then you will get the final curl. We'll skip some process here, and don't forget the axis, which is k, 1 plus 2yk. Okay, so we can write here that the projections d, okay, the projection d of S on xy plane is a circle or disk, which is basically this circle with radius 1 or equal 1 is okay. So if we are using the plane that z, let's say z is our function of two variables, 2 minus y. Okay. So the circle, it gives you the reasons that we might have using the r theta coordinates, okay, to help you out for the calculations. So the line integral f dot dr, surface integral curl f dot ds. Okay. Now since our curl f is 1 plus 2y, and then it's only on the k axis or the z axis, then as we mentioned at this part here, where is it? Here, that we might, where is it? Here, that we can have this double integrations d with respect to the area. So it's just like the green theorem all over along. Okay, so it's just like this. So we are going to write this d. Okay, so the s will be projected to this d, and we can write that curl f is 1 plus 2y and then dA. And of course this is only for a special case. I wrote that? Let me write here. This one. Okay. Okay. So for the surface that is flat, then we can write the surface integrals that will become the double integral. I think it should be d, right? It should be d. All right. So basically, we dot with k, so that's why we have this part here, 1 plus 2y dA. Now, when we have this is just a normal double integral, okay? Just like double integrals that we did in calculus. So this will be, I will write here, double integral, maybe just write regular double integral. And how to solve this is basically taking the r and theta on the circle. So here we have r is, radius is 1, or you could say it starts from 0 to 1, and then theta 0 to 2 pi. So we have a double polar calculations. So this will be 0 to pi, and then 0 1, and then we are going to exchange everything to polar. So 1 plus 2, this will be r sine theta, and this will be r dr d theta. Okay, so that's for polar. And then basically you solve this in a polar conversions, get the results, and I believe we get the results. I will skip some process. I hope you can do this, okay? Or since your finals, I will allow you to write some notes. You can write some notes from your calculus too, double polar, how to convert the double integrations, okay? So this will be equal to pi, okay, the results. Okay, if we have time, I think we can tackle some problem from the previous one, and then this also over to Stokes. Okay, now this example, okay, I think this is quite It seems like quite complex, but it's actually not so complex. So we have the supposed to be the half of the sphere, right? That we have the x squared plus y squared plus z squared equal 4. So which means that the sphere has a radius 4. And then the S is actually the part of the sphere that is inside the cylinder. So this blue one, okay, the blue color. This is something that we are going to focus on, the S, the small s. So first is we need to define the curve C. So how to deal with that is basically we have the sphere. So sphere is these equations. And then we solve with the x squared plus y squared equal 1. Okay. So let's solve this and maybe just taking subtractions to get rid of the x squared and y squared. So we have z squared is 3. So z is perhaps the intersections for z will be on the square root of 3. We are going to take the positive value. So z should be positive, okay, within this case. Okay. So we have the circle. C is circle given by x squared plus y squared equal 1. And then we have also z, plane z equal square root of 3. Okay. So that is the C, the curve C. So from this two, what is the suitable parameter? Okay. So x and y that supposed to be equal 1, what should we do is basically if we convert to polar, we will have a cosine and sine, right? Cosine and sine. So perhaps if r is in terms of x, y, z, but I will write in parameter t, we can write this as cosine, let's say t plus sine t, and then plus j, and then j will be taking the z. So we're converting this to a parameter, and this will be starting from 0 to 2 pi. Okay. And now we're focused on this parameter t, and if we derive this, we will have, so you will see that from our directions, we are going to get this r prime, or the calculation for the f dot dr, we are going to write as the f of rt multiplied with r prime t, like the line integral that you have done before. So basically, the first one, okay, is evaluating the line integral f dot dr and then change to surface integral. The second question is evaluating the surface integral and then we change into line integral. Okay, so we are taking these two sides. Okay, so this part here, we are, let me write the surface. This should be equal line integral f dot dr, which is in our line integral at the early introductions, we have that this will be f r of t and then r prime t dt. Or if you want to maybe write in more clear to see the chain rule, and then it will be very obvious, then we have this. But then we have t, that we define t from 0 to 2 pi. So we need to define the parameter first, okay, for this line integrations. And then since we have the f is defined with the example here, the information, so we can basically rewrite this xz, yz, xy, they are all in terms of a polar now. So let me write the f. Okay. F is xz plus yz plus xy. So we are going to write this, taking that the x will be cosine t, so x will be cosine t, y will be sine, and z will be square root of 3. And then this should be, let me write in prime. So dot r prime t, okay, dt. So basically we exchange the f and then plug in the r, or basically maybe taking r from this and then plug in into f. So take r of t and then take dot r prime t. Okay. So this will be 0 to pi. This will be negative square root of 3 sine t cosine t, and then plus square root of 3 and since the dot will be only having 2 axes for the r prime, so result will be the k or z axis will be 0, so we only need the first 2 axes. So we have this will be sine t cosine t, so they are going to be cancel each other, so this will be giving you the 0. In another way, we could also see that this S is a horizontal plane, right? Or part of horizontal plane. And then we have the normal, let's say here, which is, it's only just the z, right, on z axis. So it doesn't give you any like direction slope specific. So you just go up on z directions. So we can write this as well. So if we calculate the curl f, so curl f, so this is alternative. The curl f, so del cross f. So after we calculate, we have this is x minus y. Okay, and then we can take this curl f and suppose that this s, let's rewrite with s1. That basically the plane. Suppose that the plane itself is, let's say s1, okay. And then this will be equal to, we can write with the n dot n ds. Okay. So basically we see that this will be x minus y I plus x minus y j. We dot with k, and since they are basically each one of the equations, they are not matched in the axis, which will be 0, right? It will be 0. So this will be 0. Okay. So same conclusions. Okay, we still have some time, so I think I will review some exercise. So since we are in the Stokes theorem, I think we can focus on Stokes. I think to make our focus for Friday class easier, maybe I will add maybe just one additional video, maybe 10 minutes, just to make sure that that's the introductions. And then on the Friday, I will just finish off that part, and we have a practice. Okay? So my assignment, give you the one video and maybe like 7 or 8 questions exercises. I will choose the questions. Okay, so let's go for some exercise. I have prepared here. So the first part of questions on the top is evaluating the surface integral. The second part, which is the bottom one, is evaluating the line integrals, which basically they are going to be equal with each other, but how to convert both of them. So I think we can start maybe let's start from this one first, okay? Because I think we should start with this, the evaluations for f.dr. Okay, we can start taking this into our questions. So we have f vector field, okay, that is the vector field, and then we have the c. So I think we are get interested on c, right? So perhaps we can imagine how it looks like. So this will be z, x, y. So x will be, this is 1, this is 1, and this is 1. So we have a triangle here. We have a tetrahedron, right? Okay. And then what else? So okay, at least for tetrahedron, I hope you get that this will be the same with this plane, right? So if we project to xy, we will have, so project to xy. So we have, so I will take this in the normal axis. This is y, this is x. So we have something like this, right? Okay. This is 1, this is 1. So this will be, I think you can say that y is 1 minus x, right? Okay. And then what else? We can get the idea from the, let's say this is d. We can take this d. Let's say we start from constant is x. So 0 to 1. And how about y? Y will be start from 0 to 1 minus x, right? Okay? Do you still remember how to do this? In the double integral? Okay. So that will be the endpoints. And what else? So the all C will be oriented counterclockwise, which is positive, so this will be by default. Okay, so we can write down, so this is number 7. We can write down the line integral f dot dr is equal to surface integral curl f dot ds. Oh, we haven't compute the curl, so compute the curl. Curl f is, this is del cross f. It takes so much time. So I hope you can prepare your notes very well, okay? So x squared, and I don't think I can finish off by the time, so I will skip some process, okay? And maybe not showing the final result, but you have this, the curl f. Let me check the final results, okay? Do I have that? Let me check first. Yeah, I think if you compute the cross, this should be, there will be some part that will be canceling. So this will be negative 2z I, negative 2x j, negative 2y. Okay. Okay. Right. Okay, so this will be P, Q, R. And then using the z is function of two variable, and then we can write this as the this plane here. So 1 minus y minus x. So we can have the dx dy, right? Dx dy. So this will be equal double integral with respect to d. So d will be refers to our region here. So I will finish off this, hopefully. So negative 2x, and then this will be dy will be negative 1 again, negative 1, right? X is negative 1, y is negative 1, right? And z will be so this will be negative 2y. And then last part will be dA. And this d, we can use this d here. Okay, so we can start from, this is x, and this is y. And solve. Okay. So that's it.